Good morning, AM community. My name is Tobias Fiedler. I'm the Global Digital Engineering Manager for John Deere, and I will fill your next 15 minutes with the printed tractor. But first, let's see what actually John Deere is. The John Deere headquarters, or it's a US-based company. The John Deere headquarters is in Moline, Illinois. We have about 80,000 employees. We have a net sales of around 52 billion, with a net income of around 7 million. Our CEO is also called John, not John Deere, but John May. That helps, I guess. For the portfolio, a lot of people would get Deere just in contact with the tractor. That's not the case. We have agricultural equipment, as you can see on the top, with tractors, sprayers, combines, everything you need around the life cycle on the field. We have the construction equipment, which is not very well known because it's mostly sold in North America and South America. Nevertheless, Deere acquired the Wirtgen Group, which is a German company or German group of companies a couple years back. Turf equipment is known by everybody that is maybe playing golf. Forestry equipment, financial services, power systems. So we make our own engines, 4.6, 8-liter or 4.6, 8-cylinder engines that fuel and power our own equipment, but also other OEMs like maritime applications. Intelligent solutions I'll cover in a minute. Worldwide service parts is one important thing to know. Basically, is that John Deere has a 24-hour or next-day delivery promise of service parts. So that's getting us into some trouble if you think about manufacturing. Our global footprint, we have about 100 locations or more than 100 locations worldwide. 76 of them are manufacturing sites, and they are in 16 countries. If we huddle back to Germany, it's 9 factories within Germany and 19 within Europe. Covering today more on the agricultural piece or on the tractor. I guess you remember the days you were actually able to repair your own car. Those were nice days. That's not true for a tractor today as well. There's more screens and controllers in a tractor than in your car. There's more buttons, joysticks, and levers. There's, of course, Bluetooth, Wi-Fi, 4G, but there's also a high-precision GPS communication, which allows our vehicles to drive with a 2.5 centimeter accuracy down a field, turn around, come back, and all you actually have to do, because the vehicle is driving autonomous, is you're sitting in the vehicle in order to supervise the vehicle or at some point maybe to step on the brake. Also, talking about digital or intelligent solutions, the digital twin as well as the real-time health monitoring of the vehicle is of course on your phone. But let's stop talking about the Tesla of the field and let's get into additive manufacturing. We, as modern, basically as our tractor, is also, of course, our production facilities or our process production steps. So Deere has a clear strategy to implement additive manufacturing. On the left-hand side, to explain that, we use the 3-horizon model of McKinsey, and on the right is basically the systems engineering approach, and we mix that together. So we have the Horizon 1, which is the large, tall, orange side in the systems approach. It's basically everything that we have for production around tools and fixtures, and it's basically covered with existing, known, and manageable AM solutions. Horizon 2 is something around the prototyping and testing area, and we'll usually try to push the boundary in that horizon to also understand new or cutting-edge technologies for 3D printing. And then Horizon 3 is basically covering from everything from the first idea of a product, going through the design process into production and into service parts. And that's, of course, the most difficult one, and that's where we actually also do some research. And that's also where we have a success story to show today. And it's always good if you present on the second day, because you can actually then see what people talk about on the first day. And I heard a lot of questions yesterday. What is the right part for additive manufacturing? So how did we approach this? Again, you just saw the V model of the systems engineering approach, and we decomposed our product, in this case the tractor, into the 9 subsystems. And each of these subsystems has another 4 to 7 subsystems included. And then we looked at these subsystems with the potentials that these subsystems have linked to an AM potential, like mass customization, fluid flow, so the different things that basically say, okay, have we something in this bucket or not? And our findings are, for the tractor, is that there is subsystems that do not have any application to additive manufacturing, but about 1/3 of all the subsystems have a larger or smaller portion where we have an AM potential that we want to reach. But if you want to strive for potential, you usually also have some challenges. And this slide is actually from the AM forum in 2021. It's still valid today. And if we start on our 3 challenges on the left, we have the design and knowledge transfer. So 3D printing allows completely new design thinking. Again, fluid flow, lightweight, but it needs a lot of teaching for design engineers that have done the well-known design steps of the last decades. But it also needs the design engineers to understand the manufacturing technologies that are available. For Deere, it's a little bit harder. So for John Deere, it's a little bit harder because, for example, some criteria don't apply, like lightweight is usually something we're not really looking into. Nevertheless, we started with design studies, with design guidelines to foster and to unlock our design freedom. The second challenge is the size constraints. So with John Deere, as I showed, we have a large variety of products, from a small sit-on lawnmower to a large tractor. And as it's usual with small and large products, is that small products have a higher production volume and large products have a lower production volume, which brings us to the opposing factors of size and production volume, which is not favorable in this case for additive manufacturing. So we need to expand the build envelope so that we can also print large parts, which mostly apply to our low volume equipment. Third challenge is the cost of manufacturing. It's of course the biggest challenge, and especially for metal printing. Nevertheless, we highlighted that block in red. Why? Because it's what we want to talk about today, that we have one example where we solved all of these challenges and actually got in a Horizon 3 system part. And we did this with the metal binder jetting process. Metal binder jetting is a multiple step 3D printing process, and it has high processes to cost reduction compared to other additive manufacturing processes. And that's also what AM Power stated in 2018, and that's when we started looking into this kind of technology. Again, saying with this Horizon 3 approach, we usually try to see what's out there that we can leverage. We unlocked the benefits through a partnership, and that's, I guess, what was also shown yesterday a couple of times, that we don't solve our problems by ourselves. We usually reach out to partners, people that have a special knowledge in these areas. And so we partnered in this specific case with HP that introduced their metal binder jetting HP Metal Jet solution. And then as a second partner, we had GKN that just have a lot of experience in sintering and AM manufacturing. So what we do, we brought, it's called a thermal diverter valve into serial production. It's a special application for low temperatures. That's why the vehicle here is driving in snow. What does the valve do? It basically bypasses diesel, so that the fuel doesn't gel up at really low temperatures. So it's for a large vehicle, but it has low sales rates. And that's what basically was important for us, that we just had limited volumes in that case. It was hard to source with conventional technologies, and our objectives were to decrease the complexity, to decrease size, to improve the serviceability, and to have a cost competitiveness. This is the part we're actually talking about. On the right, you can see the printed part, the sintered part, the machined part, and then how it's finally assembled and would be in a vehicle. And what are the results of that part? We reduced the parts by about 20% that we need for that assembly. We reduced the size by about 60%. We passed all the quality requirements that we have internally for this part. And we actually had what we were looking for in a Horizon 3, an agile product development, and I'll cover that in a second. So it's basically, it was introduced into production in 21, and we sold around 3,000 units since then. So this shows additive manufacturing unlocks more agility. What does that mean? So conventional manufacturing has usually the transitioning from prototyping with the agile development circles. And then basically there's a transition to production technologies. And using basically the metal binder jetting process, we were able to quickly iterate already in early stages of development. It was an agile, tool-free, and a digital process, and we stayed without any transition on the same manufacturing process that fuels the assembly line today. Of course, not only our products are smart, our manufacturing is smart, but also marketing and public relations are smart. So if you want to see that story, it's on YouTube. And I guess if I would be a good influencer, I would have to say now, don't forget to subscribe. So let me summarize. We named and explained the 3 challenges we have: design and knowledge transfer, size constraints, and cost of manufacturing. And the message here clearly is, again, we need partners. We need you. I need all of you to help us to take the hurdles we face on our way to solve these problems. Nevertheless, the slide is from 21, and so of course I didn't look at the slide for 2 years. We did start also with the other 2 buckets, and for the design and knowledge transfer, we got into a publicly funded project called Digi AutoFab, which is scaling additive manufacturing usage for service parts. And in the second bucket, the size constraints, we are investigating currently new technologies for large polymer components with a company called Cubic 3D.